Hi, in this video I'm going to explain the first example of related rates of change, this topic. Let's start right away. Here it says a forest fire spreads following the form of a circle whose radius changes at a rate of 1.8 meters per minute. Now, at what rate is the area in fire growing once the radius reaches 60 meters? Now, for the purposes of being more dramatic, I added this picture on the right, showing this wildfire, this forest fire. But the thing is, in any case, we have to start by doing pretty much the same question. What is the mathematical meaning of all this? I'm actually going to sign this up here. Now, what is the mathematical meaning of this? We are requested basically to find the rate of change of the area with respect to time. The area in fire is growing due to the wildfire. So it's growing in time with respect to time. It has to be something pretty much like this. Would be a difference of area, a change of area, over a difference in time. So this is a rate of change. This is a rate of change, and we have to find this through what we have here. Now let's start by saying out something. We have this growing up as a circle. So the area of a circle, I believe everybody should be quite familiar with this. The area of a circle would be pi times the radius squared. Now, but in this case, both the area and the radius, they are not remain unchanged. They are changing when respect to time. In other words, say this whole expression, it's implicitly a function with respect to time, but we have here two variables. So this area, it's actually an area with respect to time. Now this radius is as well a area in terms of time. So this radius is actually as well changing in time. This makes sense because the more this wildfire grows with time, the radius of this area in fire will be bigger, and so will be the total area, of course. Now, once we sign this out, I'm going to take, in order to find a rate of change, we basically have in every case take a derivative. So I'm going to start to say, well, I'm going to start better below here. Will be the area, it's equal to pi times the radius squared. So I'm going to take derivative in here. But this is a function. This is a function with respect to time. Respect to time. Well, actually, this looks pretty ugly. I better write it in a simpler way. I'm going to say, well, this is a function. I'm going to call it f in a more general sense. This is an f of t. This is a function with respect to time. But we have this variable and this variable, area and radius. So if I take the derivative out of this one, the derivative of a, it would be just the same as taking the derivative of x. X prime would be just 1. In this case, it would be, for a would be here, the derivative of a will be 1. But as this is a function, it's changing with respect to time, we have to add, in this case would be a dA over dt. This is the rate of change actually that we're looking for. Now I'm going to take the derivative of pi times radius squared. This would be just the same as saying this is a constant, this is a variable, so it will be pretty much like saying, oh, I have 3 times x squared, so I'm taking the derivative of this one, will be 2 times 3 or 6 times x. So in this case, this will be 2 times pi times the radius. But here again, this is a function with respect to time. So we're going to add here, in this case, dr over dt. Now this dr over dt represents the rate of change for the radius with respect to time. The radius with respect to time, this one. And we are requested to find this value actually. Now first I'm going to simplify this out, just taking away taking away this one, just because I'm very fond of simplifying stuff. There it is. This dr, I'm sorry, dr over dt. Now let's see. This is a rate of change for how much the radius is changing with respect to time. Actually, here we have this information. The circle, whose radius changes the rate of 1.8 meters per minute. So this is actually how much the radius is changing its length with respect to time. This is actually our dr dt. So this one would be with our 1.8 meters. This would be meters over minutes. In this kind of exercises, the meters, the minutes, they do matter. They do matter a lot. So, well, let's say we are requested to find basically this rate of change, and we have here the rate of change for the radius and time. And what other information we have? We are requested to find this dA over dt exactly once the radius reaches 60 meters. In other words, once the radius has a value of 60 meters. So here in this case, we're going to substitute, and at the same time, do not forget about the units. Units are very useful not only for correctness sake, but because very likely you will find that your result is, it's very likely to be right once you notice what happens with the units. So here will be 60 meters times 1.8 meters per minute. Now, in this case, I'm going to continue here on the right below this image, this dramatic image. So, well, let's see, I'm going to put it over here. So we know that dA over dt. Now, if I multiply this 2 times pi times 60 times 1.8, I already done it here in my calculator. So this is 678.58. Now, if I multiply as well the units, meters times meters, this the first one will be like meters over 1. So if I multiply meters times meters, and the other one is over minutes, I will have meters times meters would be meters squared over minutes. Now, as you can see, this makes sense with the question that we have requested for. These meters squared has to be because we are requested to find a difference of area over a difference in time. So our units make sense, and this is actually the final result. So just going to sign here, this is a final result, and this is in terms of trying to explain this on the given context. Taking this out of the mathematics would be how much the area of this forest fire is growing with respect to time once it reached the radius reaches the value of 60 meters. So how fast is growing with respect to time once the radius reaches the value of 60 meters. Well, basically that would be it.